talking about transformations again. Now, we've talked about transformations like 18,000 times, it feels like at this point, between me and your Algebra 1 teacher. Yes, we are still using the same vocabulary. We are just applying this vocabulary to a new function. We're going to apply it to both the exponential and logarithmic functions because these are inverses of each other, so they're very much tied together. On the front page of this notes, it's going to be all about exponential transformations. And I want you to notice a few things. Number one, with your highlighter right now, I want you to highlight the base, which in this equation is e. Remember, e is a number. That base could be anything at all. It could be a 2, it could be a 1/2, it could be a 5. But we're going to use e because it's the natural base, so you see it more often in math. Notice also that the air quotes inside of the function for all of our transformations that happen inside, that is going to be up in the exponent. So let's write that down. So this all in the exponent is inside. So when we look at inside versus outside transformations, we're talking about, is the number that we've changed in the exponent or is it not in the exponent? So it makes it really easy to find your inside and outside transformations. One more thing we need to think about before we really get started is what the shape of a typical exponential function looks like. So a typical exponential function, especially for growth, which is most of the normal ones, is going to look something like this, where it's growing exponentially. That is the shape that we're going to be changing for these notes. We're going to be shifting this curve up, down, left, right, flipping it over different directions and stretching it and shrinking it. But that's the shape that we're changing this time. What's nice about transformations is the vocabulary is the same no matter what graph you're talking about. So when we're talking about transformations, we still use the vocabulary that we always have. For example, a horizontal translation is the type of function or type of transformation that's going to move my graph to the left or to the right. That has always been inside the function. So notice that the number we're changing is inside the exponent. That's how we show it's inside. Now those parentheses are not always going to be there. It's nice for them to be there, but if you notice in the two examples we have written here, do you see how these are not in parentheses? That's technically okay as long as they're still small and floaty. If they get too big, it doesn't look like they're in the exponent anymore, so that's wrong. But what we notice is that because we have a -2, that means it's going to go to the right 2 units. And because we have a +3, that means it's going to go to the left 3 units. Same rule as always. Minus moves to the right, plus moves to the left. If you want to write that down, that might be something good worth writing down. So minus is to the right, plus is to the left. Same rules that we've always had. Now my vertical translations, again, same as we've seen before. My vertical translation is just going to move the graph up or down. This number is added or subtracted behind the function, not inside of it, so it is not in the exponent, and it is big like a regular number. In my examples, you have +7, which means it's going up, and you have -1, which means it's going down. So for this one, up is plus, down is minus. But notice again, those numbers are not in the exponent themselves. Good morning. It doesn't matter. We still have our reflections, which again is something we've talked about before. We can reflect or flip this graph over the x or the y-axis. If it is flipped over the x-axis, that negative sign is in front of the base and the power. If it is flipped over the vertical or y-axis, the negative is in the exponent. So it's just negative x instead of negative base to the x. And like it doesn't get more complicated than that. So your minus sign in front is over the x-axis. Your minus sign inside is over the y-axis. Does this vocabulary sound familiar? We've talked about these before. I hope so, because we've talked about them before. The next one is called a horizontal stretch or shrink. This is the confusing one. Horizontal is on the inside, which also means that it's the opposite. So when we find a number multiplied by x on the inside, potentially in parentheses, we use the reciprocal to talk about what's happening. So if you see a 3 in the exponent, it's actually a shrink by the fraction 1/3. I flipped that number over. If you see a 1/2 in the exponent, which I know is kind of confusing looking because it's big, it's whatever. I know that it is confusing looking. Since that's a fraction, you would say that it's a stretch by 2 because you flip 1/2 over to make it 2/1. Now, last but not least, we have our vertical stretches or shrinks. And my vertical stretches and shrinks come from the number that's multiplied in front of the function, not the base itself, in front of the base. Not the base itself, but in front of the base, which means we have like a 4 in front of the e. That means it's going to be a stretch. Okay, so that 4 in front was a stretch by 4. We didn't flip this number because it's from the outside. The only number we have to flip is the inside numbers. And again, if you have 1/5, that's called a shrink by 1/5. We don't have to flip the numbers. My fraction numbers are shrinks. My large numbers that are bigger than 1 are stretches. Again, this is the same vocabulary that we've had this whole time. It only changes which function we're applying it to. And in my mind, the only way that makes this a little bit complicated is that your bases will never change from f to g, but your bases from problem to problem might be different. What I mean by that is, if you notice in examples 1 and 2, oh, by the way, I guess I should say something about this. You have this visual here. I know we've seen this before for other functions. We've applied it to bases and powers here, so you can kind of see the same visual that we've been seeing when it comes to transformations. But in numbers 1 and 2, these have transformations, but they are different bases technically from each other. What is the base used in problem number 1? Base meaning the number in the parentheses. 1/2. Do you notice how 1/2 does not change from problem to problem? It should not. If it does, something is wrong. They're not the same type of function that we've transformed. You've completely written a new function. In number 2, what is the base? 2. Again, from f to g, it has not changed. It should not change. The things that change are the numbers surrounding it. So if we go look at problem number 1, comparing f to g, we just want to describe what's happening. What are the differences between the way f is written and the way g is written? It has a negative in front. Very good. What else? Yeah, it has a -4 behind it. Those two things are transformations that are out of our table. What is it called when you put a negative sign in front of the function? Reflection over which axis? Over the x-axis. Very good. That's my first transformation, is that it is a reflection over the x-axis. What does that -4 at the very end do? How does it move when you subtract a number at the end? Say again?
1 unit down.
1 unit down. And by 1, you mean 4. Because this is a 4. But yes, subtracting numbers at the end moves it down, and it moves it down specifically the number that is there. Voila! This graph will have taken the parent function of 1/2 x, remember the base never changes from f to g, and it will have flipped it over the x-axis and moved it down. So in a visual, you should be looking for a graph that's lower, because it moved down, and flipped over, a reflection. If we look at option 2, or problem 2, option 2, the base is 2 and the base should not change. The base never changes from problem to problem from f to g. What are the differences between f and g? The +3. Okay, great. So we'll highlight the +3 because we know that's a difference. What else is different? The 4. So we can look for where these places or where these numbers are placed based on my table there. If there's a 4 in the front, what is that called? Yes, specifically a vertical stretch by a factor of 4. Very good. Whatever number is there. That's going to be your biggest hint on your homework. It's going to ask you to label the transformations. And obviously, it's like the drag and drop questions. So it's talking about the transformation when you see that word factor. That just means, what am I multiplying by? 4. What does that purple plus 3 do to my graph? If minus 4, and this one moved it down, it's going to move up 3. So again, I'm just looking for where these numbers have been placed in the transformed graph. You can refer to your table every time to see what it is talking about. So the 2 types of questions you're going to see today talk about describing transformations, as well as number 3, which asks you not only to describe it, but to write a rule, which means write an equation. We want to write an equation such that g of x, that's the name of the function g, is a reflection over the x-axis, followed by a translation 4 units to the right, and then 3 units down, of the function f of x equal to 2 raised to the x power. So if we start with this function, we want to do a bunch of things to it so that it will be a reflection over the x-axis, a translation 4 units right, and then 3 units down. So we just have to know where to put the things in the equation. The way I like to start these problems is writing f of x, or sorry, not f of x, g of x, because we named it g, equal to, and then put the base and put the power and give yourself some room in front and give yourself some room in the exponent. Now, I put the number 2 in parentheses to protect it. Because if we put a number in front of it, then it would have to have parentheses. If I put a negative in front of it, it would probably have to have parentheses. So I like putting the parentheses to protect it. If you're doing a homework problem and it's counting it wrong and you're pretty sure it's right, Big Ideas sometimes doesn't like those parentheses. Whatever. I accept the parentheses. Okay, if we want to make this a reflection over the x-axis, what do I do to this? Where? Very good. All right, so there's my negative in front. I have reflected it over the x-axis. The next thing I want to do is move it to the right 3 units. Now, right is a horizontal direction, which means it needs to go inside. So in the exponent, I'm going to put minus 3. Because putting minus 3 in the exponent is going to move my graph to the right. That's the inside of this function. If then I want to move it down 3 units, I don't do this in the exponent anymore. How do I move it down 3 units? Outside. And what do I put? Plus 3 or minus 3? Minus 3. There you go. Now, if you don't like the way this looks because you're like, I got a minus 3 and a minus 3, it is nice if you put the x minus 3, that's the exponent, in parentheses. Again, Big Ideas may not accept that, which means you just take the parentheses away and make sure that the x minus 3 that you intend to be the exponent is small and floating. It just looks kind of weird in this format because you got numbers following numbers without parentheses. With what? Which part? Why is the minus 3 in the exponent? That's a great question. Thank you for asking. So in this problem, oh, it says 4 units to the right. You're not going to stop me when I do silly things. What should this number be? 4. That's embarrassing. Sorry. Was that going to be your question? Yeah. That's just me. My bad. Okay, these are the same types of questions And this is the same kind of chart we've had for almost every function that we've studied in this class. So this vocabulary still follows us. Are we good to go to the back? Great. On the back of this, you'll notice that it kind of looks like I copy-pasted the notes from the front. However, these are transformations of logarithms, not exponentials anymore. So the function we're using has changed from having a power to having that log for logarithm. Logarithms, in my mind, are a little bit simpler because their inside is always going to be inside parentheses. Like typically that's what we see is inside parentheses. So this is again more typical of what we will see. But the vocabulary is exactly the same. Horizontal translations happen inside the function and go the opposite way, which means if we see -2, that's 2 units to the right. And if we see +3, that's 3 units to the left. So again, just like before, right is a minus sign, left is a plus sign. It's exactly what we did before. It's just a little bit simpler here because the inside is very obvious for us. Our vertical translation, again, are going to shift the logarithm graph up or down, but this is normal. Plus goes up, minus goes down. Now I'm going to make a big stink about this for a little bit. What's the difference between these ones I've highlighted in blue and the ones I've highlighted in purple? One has parentheses, the other one doesn't. If you're trying to tell me that something's moving left or right, that number has to be in parentheses next to logarithm. If you're trying to tell me that it goes up and down, it cannot be in parentheses. Because right now, these numbers are technically outside of the logarithm. Because the logarithm of x is the only part. This is the logarithm of x minus 2. So the parentheses are 1000% important here. But reflections work essentially the same. Our reflections flip over the x or y axis depending on where the negative sign is. But if it's in front, it's the x-axis. If it's inside, it's the y. And it really doesn't get more complicated than that. That's the same rule as always. Our horizontal stretches and shrinks are still equally confusing because that number is multiplied on the inside. Notice the parentheses came back because it's inside. But again, we flip the number over because it's horizontal. So 3 is going to be a shrink by a third. And 1/2 is going to be a stretch by a 2. We flip the numbers. We use the reciprocal. Our vertical stretches and shrinks still go outside the function in front. So there will be numbers in front of logarithm. So like the first one, 4 log of x is a stretch by 4. 1/5 log of x is a shrink by 1/5. So that one is not all that confusing, just like normal. So on logarithms, just make sure you know when to add parentheses to the x or not. Basically, if you are doing a horizontal transformation, it goes in parentheses. One thing I didn't talk about before we really got started on this is what a logarithmic graph actually looks like. And we talked about this last class, but it wasn't all that clear, I don't think, because it was kind of tucked in our notes with other stuff. The graph that we are switching around is going to look something like this. So that is the starting graph, log of x-ish. It's a sketch of it. And that's the one that we're going to be flipping, moving up and down, or stretching and shrinking. So it is not the same as an exponential graph. Exponentials go up like normal. Logarithms have a boundary on the right side or on the left side. Exponentials have a boundary on the bottom. So we just have to make sure we recognize the shape so we know what it should look like when you transform it. We have the same visual concept for you. I think we like looking at these. We've seen this before, but now it's just applied to a logarithm. This one is way more normal, like the other things that happen. So let's describe our transformations. Again, just like exponentials, the base should never change. The base of this logarithm right here, because I don't see anything written, what is the base? 10. It's a common logarithm, base is 10. Notice that the base did not change. The base should not change. If it changed, something happened. You did something wrong. We did something wrong. The things I notice in this problem that are different are, number one, that there's a whole negative sign now inside, and there's a whole 1/2 inside. Those two numbers that have been changed from F to G are going to do two transformations to my graph. If there's a negative on the inside, what is that transformation called? It is something horizontal-ish because it is on the inside, but since it's a negative, it's definitely a reflection. It's just over the opposite axis. So not over the x-axis, this one's over the y-axis. Horizontal is inside and opposite, so instead of x, it's y. Ooh, but the 1/2 is multiplied on the inside. This is the confusing one because we don't say that this is a something by 1/2. What number am I using? 2. Very good, with a reciprocal, which means that this is a stretch by a factor of 2. Because it's the flipped version of that number. When the flipped version of that number is a big number, it's a stretch. When the flipped version of that number is a fraction, it's a shrink. So again, this is just like the other side. I think logarithms are a little bit simpler because there's a full-on inside. And I don't have to write small floaty numbers. If we look at number 5, first things first, what is the base of this logarithm? 1/2. Did the base change from F to G? No, good. It shouldn't. It can't. What did change from F to G? +4. And that +4, is it on the inside or the outside? Inside. So we know it's going to move horizontally since it's on the inside. Notice the parentheses showed up. That's why we know it's inside. Which direction does it move inside if we do +4? It is to the left specifically. Yeah, it's left or right when it's horizontal and inside. Plus is to the left. So this is going to be a left 4 units move. So we've taken that logarithm and we've just moved it to the left 4 units. Again, the kinds of questions you'll be asked to do are describing the transformations as well as writing a rule. So we're going to do the same thing like we did on the front. We're going to write an equation for g of x so that it is a vertical stretch by 2 followed by a reflection over the x-axis and then a translation 4 units up of f of x equal to log base 1/3 of x. Should that 1/3 ever change? No, don't ever change the base. We're just changing the things around the logarithm. So again, if I was setting this one up to work it, and I'm going to have to zoom in a little bit just so it's not so far away. We would have f of x, I did it again, g of x equal to, and this is how you start. You set up log 1/3, leaving a little bit of room in front. And then I like to go ahead and put my parentheses when I'm writing the function itself, just so I can know what's inside and what's outside. If you're doing your homework and Big Ideas doesn't like it when you type the parentheses, try it without it. It's just depending on how they've coded the computer. Okay, if we want to take this logarithm and we want to stretch it by 2, where do I put the number 2? Look for the words vertical stretch on your table. Where are those numbers?
Inside.
Vertical stretch?
In the front.
In the front. So I'm going to put that 2 in the front. Hooray, I have vertically stretched it. If I want to reflect this over the x-axis, where do I put the minus sign? In front of the 2. Very good. And if I want to translate this graph up 4 units, Does up go inside or outside?
Outside.
Outside. Up is a plus direction, so we just put +4 on the outside. Now there's nothing else going on. There's nothing really happening on the inside of this function, so I just go ahead and put my x back. I leave that space kind of open because you might have more numbers on the inside of that logarithm. So what you do when you're doing these problems is you just kind of add on the different parts as you read them. Now you must do them in the order that you read them so that you make sure that you're doing each in the correct order. How do we feel about this? It's okay. I'm glad it's just okay because that means that we need to practice. The way that we're going to practice today is with a gallery walk out in the hallway.